Hey everyone, in this video I'm going to show you how to remember the 6 basic trig integrals that you're introduced to in Calculus 1 or in AP Calculus AB. Let's get started. First of all, we have the integral of sine of x. This integral right here, if you know that the derivative of sine of x is cosine of x, and you know that the derivative of cosine of x is negative sine of x, you can kind of see that the antiderivative of sine of x is simply going to be negative cosine of x. And just add your plus c. That's the first one. And like we just said, the derivative of sine is cosine, so the integral of cosine has to be sine. Now, you're going to be like, okay, that's pretty easy, but what about the other 4? Well, let me tell you this. All you have to remember for the other 4 are just sine and cosine. Literally, all the 6 basic trig integrals can be expressed in terms of sine and cosine. I'm not capping. Let me continue. The integral of tangent of x with some disrespect to x. I'm going to say disrespect because tangent is an interesting function. The antiderivative of tangent of x is negative natural log of the absolute value of cosine of x plus c. So I've also seen this expressed as a natural log of secant of x plus c, absolute value, by taking this negative and moving up to the exponent and using the identity that 1 over cosine is secant, because you can move the negative power as a fraction, which makes sense. But I'm going to leave it in this form on purpose. Then you have the integral of cosecant of x dx and the integral of secant of x dx. We're going to get back to those, but we're going to answer this integral down here. The integral of cotangent of x dx. This is equal to, it's another natural log, absolute value of sine of x. And you add c. That's that. Now, these 2 trip up students the most, and they cause the most memorization. You might see the integral of secant of x dx, for example, expressed as the natural log of the absolute value of secant of x plus tangent of x plus c. I'm not going to use that antiderivative, even though that is correct. I'm actually going to express it this way. The integral of secant of x dx is equal to the inverse hyperbolic tangent, I'll explain what that is, of sine of x plus c. That's it. No absolute value. And the integral of cosecant of x dx is similarly expressed as negative inverse hyperbolic tangent of cosine of x plus c. And that's it. That's all you have to know. And notice, the integrals whose antiderivatives have cosine always have a negative in front. And the integrals whose antiderivative sine is always positive, right? And also notice this. The standard 2 integrals, sine and cosine, they don't have much going on, right? They're pretty basic. The quotient integrals, being tangent and cotangent, because tangent is sine over cosine, cotangent is cosine over sine, they have the natural logs. The quotient trig functions have the natural log. And likewise, the reciprocal trig functions of cosecant and secant is 1 over sine, secant is 1 over cosine, those have the inverse hyperbolic tangent. Or I'm just going to say artanh. They have the artanh function. So why does this work? Well, let me explain. So for the integral of sine of x and cosine of x, you could determine this is true by their derivatives. So I'm really not going to go over this. But for these trig functions, you kind of just remember this rough circle. You have sine of x up here. You have cosine of x. You have negative sine of x. Make sure that is a negative. And you have negative cosine of x. Because the sine and cosine derivatives and integrals are cyclical. If you want to take a derivative, you go this way. If you want to integrate, you go this way. And you just keep kind of going in this direction if you want to take derivatives, and likewise integrals. And notice the integral sign is negative cosine, and the integral will go this way. Integral cosine is sine. So that's proven. Now, for tangent. Tangent is expressed as sine over cosine. Let's prove that this antiderivative is true by rewriting tangent as sine over cosine. So we have the integral of sine of x over cosine of x dx. And this is just going to require simple u substitution. We're going to let our u equal cosine of x. That way our du is the derivative of cosine is negative sine of x. Don't forget your dx, your differential, that's very important. And notice that we have a sine of x dx, but we have a negative, so we can move the negative to the du. Kind of like this. It makes sine positive. That's okay. Now we can integrate. We can rewrite this in terms of u. We have the integral. This entire thing becomes our negative du. The entire top. This entire thing becomes negative du. And we're going to have over u's cosine. And we could easily move this out of the integral, the negative sign. So we have the negative. And we can move the du as the differential in front and put a 1 over. 1 over u du. Now the integral of 1 over u du is a standard integral in Calc 1 and AP Calculus AB. This is equal to, don't forget the negative, but the integral 1 over u is the natural log of u. Now what is u? U is cosine of x. So you get negative natural log absolute value of cosine of x plus c. And that's how you confirm the integral of tangent. Now for the integral of cotangent, we're still going to rewrite cotangent as the reciprocal of tangent, which is cosine over sine. Now we're going to do another u substitution. We're going to let u equal sine of x. So our differential du is cosine of x dx. Just by taking a derivative. We have a direct match right here for cosine of x dx. So that means we can rewrite this integral as the integral of du over u, which is also the integral of 1 over u du. And we know that is a natural log of u. And what is our u? Our u is sine of x. So we have the natural log of the absolute value of sine of x plus c. That's beautiful, isn't it? The integral of tangent and cotangent both proven. Now, what about the integral of secant of x and cosecant of x? This is where the magic happens. And why I don't tend to use the standard antiderivative that's taught in Calc 1 and AP Calculus AB. But on tests, you should, but it's good to know these two antiderivatives that I mentioned because they are equivalent, and I'll show you why. Okay, let's start with the integral of secant of x dx. Because the integral of cosecant of x dx will be very similar to this integral. First, let's just start by using the identity of secant. Secant is 1 over cosine. Let's just start with that and see if we could do anything with that. Okay, doesn't seem like it. Let's just try something. Let's multiply the top and bottom by cosine of x. See if that does anything, right? We're just trying things that seem to work. Now the top becomes cosine of x. The bottom becomes cosine squared of x dx. Now, cosine squared of x if you remember your Pythagorean identity, that sine squared of x plus cosine squared of x is equal to 1. Cosine squared of x is the same thing as 1 minus sine squared of x. That's just a Pythagorean identity. So we could replace cosine squared of x with that. And we get this. Cosine of x over 1 minus sine squared of x dx. Now, let's just try something. Let's try a u substitution. But what are we going to make our u? Well, think of sine squared of x as sine of x all squared. So we're going to make our u sine of x. So that our differential du is cosine of x dx. Notice we do have a cosine of x dx. Right there. So this integral becomes the integral of du over 1 minus u sine of x, so u squared is sine squared of x, u squared. You can move the du to the front and put a 1 over. 1 over 1 minus u squared du. Now, if you've seen this integral before, you could easily integrate this in terms of partial fractions, but I'm not going to because I know something else. I know, and this is why I recommend the Calc 1 or even the AP Calculus AP curriculum slightly reteach and maybe introduce the properties of hyperbolic trigonometry, because we're going to use a hyperbolic trig identity right now. Well, not really an identity, but more like a derivative and integral identity. The derivative, and note, this is a note, the derivative of the inverse hyperbolic tangent of x is equal to 1 over 1 minus x squared. But there's a domain restriction. This is only true when the absolute value of x is less than 1. There's a domain restriction. Because the inverse hyperbolic tangent of x is only defined for negative 1 to 1. It doesn't include negative 1 or positive 1. There's also another inverse hyperbolic trig identity whose derivative is also the same. And that is inverse hyperbolic cotangent of x, which is r coth of x. That's also 1 over 1 minus x squared. The domain is different though. The absolute value of x has to be greater than 1. Notice our integral is 1 over 1 minus u squared. These derivatives are exactly 1 over 1 minus x squared, meaning we have to use one of these. But which do we use? Well, we have to go back to our substitution. We let u equal sine of x. Our u is that. Sine of x is strictly bounded between negative 1 to 1 in terms of its range. That means sine of x can only output values of negative 1 to 1. So this u will only be between negative 1 to 1. It will also include those values. Which stays in that range? The inverse hyperbolic cotangent? No, it's outside of the range. It's always greater than 1 or always less than negative 1. What about the inverse hyperbolic tangent? Yes, because it's always between negative 1 and 1, just by this definition and by this domain definition. So we can conclude that all of this, I'm going to draw an arrow like this, equals inverse hyperbolic tangent of our u. And what is our u? Sine of x. So it becomes inverse hyperbolic tangent of sine of x plus c. And that confirms what we saw on the front. That is the integral of secant of x dx. If calculus teachers decide to introduce hyperbolic trig, in Calc 1 or EB Calculus AB, this is the definition of the inverse hyperbolic tangent of anything. We're going to call it U. And that is equal to 1/2 of the natural log of 1 plus u over 1 minus u. To prove that this is identical to the standard antiderivative of the natural log of the absolute value secant of x plus tangent of x, we're going to use this identity. So let's do that. We're going to continue our derivation. This is going to be equal to 1/2 of the natural log of 1 plus, what's our u? Our u is sine of x, over 1 minus sine of x. Nice. Okay, let's see what we could do here. What about if we, in the natural log argument, what if we multiply it by its conjugate, 1 plus sine of x? Let's try that. And using the identity that a plus b times a minus b is a squared minus b squared, the difference of squares, this is equal to 1 plus sine of x all squared. Don't expand it, trust me. And this is going to be 1 minus sine squared of x. And what is 1 minus sine squared of x? This is precisely cosine of x by the Pythagorean identity. That's nice. So we're going to draw an arrow this way. I'm going to say that's equal to 1/2 of the natural log of, and since this is cosine squared of x, I'm actually, since they both have the square, I'm going to move the square out of the cosine, so it's external, like this. Kind of like this. And since they both have cosine, you can move the square to the very outside, which is valid. 1 plus sine of x over cosine of x. Squared. Like that. Now, before we use our log properties, I have to tell you a very important exception to the log properties, but it still works. You just need to add something. So say you have the natural log of u squared. This is indeed equal to 2 natural log of u, but you're actually forgetting something. Absolute value. Why is that? Because, look, if you set u equals to, say, -3, you have -3 all squared. That's 9. So you have the natural log of 9. Okay? So you have the natural log of 9. If we plug in -3 here, we're going to get 2 natural log of the absolute value of -3, which is 2 natural log of 3. And we can move the exponent up. So natural log of 3 squared, which is natural log of 9. Exactly what we got up above. So we have to add the absolute value. So we can move the 2 to the front, and then kind of do this this cancellation of the 1/2 and the 2, but we have to turn the argument inside to an absolute value. So let's do that. Remembering this rule. Because you can move the exponent down, but you have to remember to do this. And, sorry about this, but there's a little error. The 2 shouldn't have gone on the outside. It should have stayed in the inside. Kind of like this. My fault. We're all human, so we all make mistakes. The 2 should go on the inside of the natural log. but the log property still applies. You can move the 2 to the front, but make sure to put the absolute value. So we have 1/2 times 2 natural log of the absolute value of 1 plus sine of x over cosine of x. The 2's cancel, and we're simply left with the natural log. Now notice I have the same denominator, cosine of x. That means I could split the fraction into 1 over cosine of x plus sine of x over cosine of x. Now if you know your trig identities, this is clear. We're actually done. We will rewrite the natural log. 1 over cosine is secant. Sine over cosine is tangent. There you go. Proven. This is equal to this. Just by the definition of the inverse hyperbolic tangent. We've proven it. Let's go. Now that we proved the integral of secant of x is indeed inverse hyperbolic tangent of sine of x plus c, let's prove that the integral of cosecant of x dx similarly involves inverse hyperbolic tangent as well. I'm going to start with the definition of cosecant, which is 1 over sine. This is going to be very similar to the secant integral. Let's multiply the top and bottom by sine of x. That way we get sine of x over sine squared of x dx. Okay. And we're going to use the Pythagorean identity right here. The sine squared of x is 1 minus cosine squared of x. And we're going to do the u substitution of this right here. We're going to let u equal cosine of x, so that our du is negative sine of x dx. Do not forget your negative. So I'm just going to kind of squish the negative in there. Du is negative sine of x dx. Yeah, that's a negative. That's a negative. That's a negative. That's what it is. So that means our negative du is sine of x dx. And we have that right here. So that means this is the integral of negative du over 1 minus u squared. We can move the negative on the outside and the du to the front and do the 1 thing. So we have negative integral 1 over 1 minus u squared du. If you remember from before, the derivatives, and we just write them quickly. And their domains. There we go. We have the derivatives. The cosine of x, its range is bounded between -1 to 1, similarly to sine. That means our u, the values of u are only going to be between -1 to 1, meaning it's not inverse hyperbolic cotangent we use. We use inverse hyperbolic tangent again. So this is the integral of -1 over 1 minus u squared du, which becomes negative inverse hyperbolic tangent of u. And what is our u? Cosine of x. Plus c. That's it. Now, we're going to prove that this is equal to the natural log standard textbook definition of negative natural log of the absolute value of cosecant of x plus cotangent of x plus c. Let's get started on that. Let's rewrite the definition of inverse hyperbolic tangent again. Inverse hyperbolic tangent of u is half natural log of 1 plus u over 1 minus u. And let's plug in cosine of x, but don't forget to put the negative. So we have, I'm just going to put the negative on the outside like this, kind of like that. Half natural log of 1 plus cosine of x over 1 minus cosine of x. Multiply top and bottom by 1 plus cosine of x, the conjugate of the denominator. Same thing. So we get negative half natural log of 1 plus cosine of x all squared over 1 minus cosine squared of x, which we know is sine of x. Sine squared of x, my fault. Let's continue here. This is going to be rewritten. Let's move the negative in. Negative half natural log of, this is sine of x all squared, remember? So we can square the entire thing. 1 plus cosine of x over sine of x all squared. And remembering that we can move the 2 to the front, but we have to include the absolute value around the natural log, we get half times 2 natural log of the absolute value of 1 plus cosine of x over sine of x. The 2's cancel out like we expected, and we get negative natural log of the absolute value. Sine of x is the common denominator here, so we can separate the fractions into 1 over sine of x plus cosine of x over sine of x. Now it should be kind of clear to you what we have here based on those important identities. 1 over sine of x is cosecant of x. Cosine over sine is cotangent. There you go. The standard antiderivative is proven. No memorization needed on the cosecant and the secant. None of that memorization is needed. You don't have to know any of that. There's no trick, no multiplying the top and bottom of the integral by secant of x plus tangent of x, or cosecant of x plus cotangent of x. None of those tricks. This is how those tricks were derived, from this. And going back to the very beginning, if you are taking Calc 1, I highly recommend that you remember these forms. They're going to make your life easier. They're also valid, but if your Calc teacher is very picky, you could use the standard definitions of negative natural log of the absolute value of cosine of x plus cotangent of x plus c for this, and natural log of the absolute value of secant of x plus tangent of x plus c. Same thing, but I think it's easier to remember this because 1, look, you only have sine and cosine. Sine and cosine are the easiest. And a lot of people remember their sine and cosine values. Not so much their secant values, their cosecant values, or even their tangent values. Those are harder to remember. And the pattern is clear. The cosines have negatives. The quotients have natural logs. And the reciprocals have inverse hyperbolic tangent. Let's try a definite integral example to really cement this. To show how streamlined this is, let's say we're asked to integrate the definite integral from 0 to say, let's say pi over 3 of secant of x dx. Okay? And this is a calculator allowed question. Okay? We know that the antiderivative of this is inverse hyperbolic tangent of sine of x. By the second fundamental theorem of calculus, we just evaluate this antiderivative at the bounds that we're given and subtract 2. So we have inverse hyperbolic tangent of the sine of pi over 3 minus the inverse hyperbolic tangent of the sine of 0. The sine of 0 we know is 0, and by the definition of the inverse hyperbolic tangent, if we plug in 0 to this, we're going to get natural log 1. Natural log 1 is 0. So this entire thing is 0. That means we just evaluate this. The sine of pi over 3 is a simple value on a unit circle. The sine of pi over 3 is square root 3 over 2. And this is a calculator question, so you do not need to plug it into this. This will be about, rounded to 3 decimal places, 1.317. That's it. This is it. You could actually leave your answer as this. This is valid. Or if your calc teacher says no calculator on this question, give me the simplified answer. You have to remember this definition though. And I'm going to draw an arrow this way, which is 1/2 of the natural log of 1 plus square root 3 over 2 over 1 minus square root 3 over 2. Now you kind of have to get a common denominator here. So this is going to be 1/2 natural log 2 plus square root 3 over 2 over 2 minus square root 3 over 2. Notice that both have 2's in the denominator, so actually those cancel out. So we're just left with 1/2 natural log of 2 plus square root 3 over 2 minus square root 3. And honestly, you have to rationalize this because your calc teacher might be picky. So multiply the top and bottom by 2 plus square root 3. And you get 1/2 natural log of parentheses 2 plus square root 3 squared over 2 squared minus square root 3 squared. Okay, now let's just simplify this. 1/2 natural log. We could actually expand the top. Remember, a plus b all squared is a squared plus 2ab plus b squared. So we expand the top. We get 4 plus 2ab, 2 times 2 times square root 3. And the b squared is just 3. And we have over 4 minus 3. And 4 minus 3 is 1, so that's easy. This is 1/2 natural log of just the top. 4, 2 times square root 3 is 4 square root 3. Plus 3. So you're left with 1/2 natural log. 4 plus 3 is 7. 7 plus 4 square root 3. And honestly, I think you would be done at this point. This is simplified enough for me. I would say, yeah, keep this as a final answer if you didn't have access to a calculator. But if you did, all calculators, they have inverse hyperbolic trig function capabilities. So on your calculator, whether it's a TI-84 or like a NumWorks or something, just look up your manual or look up on YouTube how to access those hyperbolic trig functions, and they should be available. That way you can evaluate this easily. But if you can't, Just have to remember the definition and simplify for the final result. But I do hope that kind of cemented the 6 basic trig integrals in your mind and shows that you really only need sine and cosine to write all these antiderivatives, the natural logs, and the new inverse hyperbolic tangents. And yeah, if your calc teacher requires you to use the textbook definition of these antiderivatives, which are the natural logs of the secant of x plus tangent of x and the negative natural log of the cosecant of x plus cotangent of x, by all means, you could use those. But if you remember this, it's going to save you a lot of time and a lot of space. See you in the next one. Please like and probably subscribe if you want more calculus content or even math content or physics content, because I'll be excited to do more physics content. But other than that, hope this helped. See you in the next one. Peace.